Good morning to everybody. Today I'd like to talk about some mathematical results about the transport properties of the Lévy-Lorentz gas. So before starting, let me thank the organizers for this invitation that I really appreciate. Okay, so this is, let's check whether, okay, yes, it works. This is the outline of my talk. I introduce very briefly the model, and then I'll discuss fluctuations in this model, both normal and the typical and large fluctuations. So in order to elucidate the transport properties of the model. As I said, today I only discuss mathematical results. Okay, so results by mathematician, not results, heuristic results and simulations by physicists. So the model. This is a model for diffusion in random medium. The model was introduced in 2000 by Barkai and collaborators and consists of certain scatters, obstacles, on the real line placed at position omega. The first main hypothesis of the model is that distances between consecutive obstacles form a sequence of positive IID random variables. And the model also consists of a particle that moves on this line and say Vn, the velocity of the particle before the end collision with an obstacle. The second main hypothesis of the model is that velocity forms a sequence of IID random variables which take only values -1 and 1 with equal probability. Okay, so this is the simplest possible version of the model. Let me sketch the motion of the particle to clarify the model with a picture. This is the line with the obstacle in red at position omega, and at the beginning you put the particle on an obstacle, say omega 0, and then I need, in order to describe the model, two variables which are Sn. Sn is the label of the obstacle at the end collision, so S0 is 0. And then I need also the time, Tn, of the end collision, so T0 is set equal to 0. Okay, so after you put the particle, you draw a velocity, V1. Okay, in this example, V1 is equal to -1. So the particle starts moving toward the left and reach the first obstacle, okay, which is omega -1. So S1 is -1 in this example. It can be written as S0 plus V1. V1 is the time of the first collision. Okay? Since the speed of the particle is 1, the time of the first collision basically is the distance between the two obstacles, omega 0 and omega -1. Okay, so the first collision occurs, and you draw the second velocity, which in this example is V2 equal to +1. This means that in the first collision, the particle is reflected. Okay, and starts moving toward the right until reach the second obstacle with the label S2, which is 0 in this example. It can be written as S1 plus V2. At the time, T2, which is T1 plus the distance between the previous obstacles, and so on and so forth. You draw V3 and you get, for example, 1. So this means that in the second collision, the particle is not reflected as before, but is transmitted and continues to move toward the right until reach the third obstacle with label S3, which is 1 in this example at the time T3. Okay, so if you like formulas, the motion of the particle at time t is described by the process xt defined this way. So this is nothing but a linear interpolation in time of the position of the obstacles. The label of the obstacle results in the sum of velocity up to collision n, and Sn is nothing but the simple symmetric random walk, according to our hypothesis. Okay, so what's the problem? The problem is to understand whether in this model superdiffusion is possible. Superdiffusion is diffusion at a faster rate than the square root of time. And so in order to have at least the hope to observe superdiffusion in the model, we need sometimes the distance between obstacles can take very large value. And for the reason, we need to distribute the distance between obstacles according to a power law distribution. And this is the third main hypothesis of the model. And so this is the tail distribution of delta 1, the distance between two obstacles, which is a slowly varying function, such as a constant or the logarithm, just to have some idea, divided by x to alpha. Alpha is the tail index. Okay, so this is how mathematician describes power law. So they allow for a slowly varying correction. This is the third main hypothesis of the model. In this talk, I only focus on the case where the expectation, the mean of delta 1 is finite. And this is the fourth and last main hypothesis of the model. Okay, mu, expectation of delta 1 is finite. This means that alpha cannot be smaller than 1. When alpha is equal to 1, the function L must ensure finite expectation. When alpha is larger than 1, L can be any. Okay, so we want to understand the properties of the motion of the process xt under this hypothesis. Actually, this is not one problem, but is two problems. Indeed, one problem is the so-called quench problem, where we discuss the properties of the motion conditional on a typical realization of disorder, of the arrangement of the obstacles. And the other problem is the so-called annealed problem, or quenched average problem, which consists in investigating the properties of the motion averaging under both disorder and velocities. So let me repeat. The quench problem is the study of the motion under the velocity law for a fixed typical realization of the obstacles. The anneal problem is the study of the process under collecting statistics under both disorder and velocity. I use a product law here, so this means that we are assuming that the disorder and velocity are. Okay, so let me motivate the problem from a physical experiment. A few years ago, physicists devised a certain optical material called Lévy glasses, okay, which allow somehow super diffusion of light. On the left, you can see a micrograph of a Lévy glass. A Lévy glass is made by a microsphere of glass embedded in a polymeric matrix. You send some light in this material and you study how light diffuses in this material. On the right, you see, sorry, oops. On the right here, you see a simulation of the path of a photon in this material. The important point is that physicists claim that they can engineer such a material in such a way the distribution of the diameters of the microspheres is power law with a given alpha. Okay, so they claim, give me an alpha, I can engineer a material, the power law distributed diameters with that alpha. And in this framework, by analyzing transmitted light in the material, they observe super diffusion when alpha is smaller than 3. Super diffusion at least on short time scales. The Lévy-Lorentz gas model is motivated by this experiment, and I want to understand whether some similar features about super diffusion can occur in the model. Okay, so let's start the study of the fluctuation. Okay, the first fluctuation one want to study are typical fluctuation. Okay? Basically, we are trying now to describe the central part of the distribution of the displacement of the particle. Alessandro Bianchi, Marco Lenci, Giampaolo Cristadoro, and Marilena Ligabue in 2016 proved the following quench the central limit theorem. Basically, if you scale the displacement of the particle with the square root of time, and you send t to infinity, you get for almost all arrangement of p obstacles convergence in distribution to a Gaussian random variable. Okay, this is the statement of a central limit theorem. The important part here is that typical fluctuation the size of typical fluctuation up to time t is the square root of t. This is the important content. From here, immediately, you get a similar result for the annealed problem, okay? If instead on a typical realization omega of the disorder, you average over disorder, you get the same convergent distribution, okay? So the central part of the distribution, both in the quotient and in the annealed framework of the displacement of the particle, displays normal scaling. There's no any evidence of superdiffusion in the central part of the distribution. In order to understand whether superdiffusion can occur, we need to analyze the large fluctuation. Okay, so let's continue with fluctuation. Let's discuss the annealed framework first. And we want to study now this probability. The probability that at a certain time the displacement is larger than x times t, where x in a number in between 0 and 1. For x larger than 1, this probability is 0. Indeed, the speed of the particle is 1. So in a time t, the particle can travel at most for a distance equal to t. Okay? So there's no reason to consider x larger than 1. This is actually a rare event. Indeed, we have just seen that the typical size of fluctuation is the square root of t. Okay? So on the scale t, if you study the displacement on the scale t, we are discussing a rare event. So this is our results to characterize such probability. I don't want to enter in all details of the results since I don't have time. I just want to, to focus on this scale factor. Okay, so if you want, the problem is to find a scale factor depending on time in such a way this probability scaled by this factor when t goes to infinity converges to a non-trivial limit, to a limit which is not 0, not infinity. Okay? If you want, if you find this scaling factor, you have understood the behavior of this probability. Okay, it turns out that the scale factor is the square root of t times the tail probability of t. Why? This is an evidence of the so-called principle of big jump in the Levi-tailed world. The principle of big jump states that if you have a sum, if you look at the large fluctuation of a sum of IID Levi-tailed random variables, such large fluctuation is realized by a large value of just one of the term in the sum. So this is basically the content of the principle of the single big jump. This is what occurs here. Why? Basically, the process xt, accumulates interdistances between obstacles up to time t. How many? In a number that is the number of the obstacles that the particle is able to experience up to time t. Okay, but recall, the process of obstacles exploration is the simple symmetric random walk. So in a time t, you are able to explore number of obstacles which is of the order of magnitude of the square root of t. So basically, the square root of t you see here is the number of obstacles that the particle can experience up to time t. And then you have the tail, the probability of delta 1. So the large fluctuation xt, the probability of a large fluctuation of xt is the number of interdistances experienced by the particle up to time t times the tail probability of delta 1. And this is the mathematical formulation of the principle of the single big jump. Okay, so this is what you basically see here. Due to the fact that one interdistance between two obstacles takes a very large value in order to realize this event, the particle can perform a long ballistic flight when it enters this gap between these two obstacles. Okay, so, and this is the manifestation of superdiffusion, at least at the annealed level. We see that the quenched situation is different. Okay, so now we have a central limit theorem to describe the central part of the distribution of the displacement. We have a large deviation principle to describe the tail of such distribution. Basically, we have all we need to compute moments of the displacement. Okay, usually physicists look at the moments in order to to assess whether there is superdiffusion or not. And this is the results describing the annealed moment. This is the annealed moment of order Q. You see that when Q is smaller than 2 alpha minus 1, we have the normal scaling of the moment. When Q is larger than 2 alpha minus 1, we have a scaling exponent which is Q plus 1/2 minus alpha. Minus alpha comes from the tail distribution of delta 1. And we have a superdiffusion, okay, a superdiffusive scaling. If you set Q equal to 2, you find the scaling exponent of the mean square displacement, okay, which for alpha smaller than 3/2, so for alpha smaller than half, is a superdiffusive scaling exponent. So is an exponent larger than 1. What about the quench problem? The quench problem is completely different. If you study the large fluctuation conditional on a typical realization of the obstacle, you don't find, as before, a decay of probability which is polynomial. You find a decay of probability which is exponential. Actually, a stretcher exponential with stretching exponent 1. The point is that you move from a polynomial decay to an exponential decay. Okay, the things change completely. How to look, if you take expectation of this probability with respect to this order, come back to the probability of the large fluctuation in the annealed framework. How to reconcile this exponential decay with the polynomial decay we saw before? The only way to reconcile the two results is that there are some samples omega whose time needed to enter the exponential decay is arbitrarily large. Okay, so I don't want to discuss the tree model. You can now compute moments in the quench framework, so conditional on a typical realization or disorder, and due to the fact that the tail decayed exponentially fast, we found normal scaling for all order of the moments. So in the quench scenario, there's no superdiffusion at all. And this is a picture in the Pareto case with alpha equal to 2, showing that in the quenched framework, moments have an initial superdiffusive growth which develops into normal scaling after a while. So, in conclusion, this model displays superdiffusion in the annealed framework, but not in the quenched scenario. Actually, at the level of individual samples, an initial superdiffusion